This section explains what the ancients knew about energy. Energy conservation is true and, alone, nearly useless. It permits the rock to leap from warm mud back into the cold sky, yet that never happens. The ancients' real discovery, sharpened by Joule and Helmholtz out of Thomson's cannon boring, was that heat is energy, and that the conversion into it runs one way. Work becomes heat freely. Heat returns to work only partially. So, the conserved quantity conceals a second, directed variable, the quality of energy, its capacity to do work, which only degrades. This asymmetry is the whole book in miniature. A steady through-flow of high-quality energy, degrading as it passes, is precisely what lets a living thing leave increased order behind it, rather than decay. This section explains the first law of thermodynamics and the gap it leaves open. Energy is conserved. The rock's potential becomes kinetic. Friction converts mechanical motion into heat, and the books always balance. That is the first law, and Chapter 1 establishes it as necessary but mute. The step that does the work is the gap. The law leaves behind. A rock plopping into mud violates nothing, yet no one has watched warm mud spit a cold rock back into the sky. Conservation cannot tell you which way a process runs. So energy must carry a second attribute, its quality, high in sunlight, poor in heat, that degrades one way in every transaction. The chapter's slogan, that the flow of energy can leave behind increased order, plants the book's whole thesis. Directional degradation is what powers ordered life. This section lays out what this chapter is for, and the three ideas it seeds. Chapter 1 sharpened the puzzle, order arising with nobody running the factory. This chapter's move is to refuse a single answer. It lays out instead the hierarchy of scales that every later mechanism will inhabit, from the protozoan down to the DNA helix. Each level's governing principles emerge from the one beneath, yet differ in character from the one beneath, yet differ in character from it. This chapter is the book's orientation map, not an argument. There are no formulas. There is just the vocabulary and the icons you flip back to. 3 physical ideas. Seed everything downstream. Bilayers self-assemble into compartments. Active. Transport routes products to their destinations. Enzymes enforce specificity. The generative primitive is this. Order without a controller is a scale emergence phenomenon. It is distributed across levels, never imposed from one. This section plants the central question. The book will spend its 10 chapters answering. No one is running the factory, yet the cell builds, sorts, and regulates itself flawlessly. That is the puzzle. This no formula orientation chapter raises before the answer arrives. The answer is already named here as 3 purely local mechanisms. Bilayer membranes that self-assemble from their own molecules, active transport that carries cargo to its addresses, and enzymes that recognize one target and ignore all others. And enzymes that recognize one target and each molecule sits. The second primitive is the scale ladder, running from atom to molecule to organelle to cell. At each level, the governing principles emerge from the level beneath, yet differ in character from it. Order without a foreman, and law changing flavor with scale. This part explains the single move that runs through the whole chapter. Macroscopic law is the statistics of microscopic chaos. Heat has no substance to it. It is random molecular motion. Every air molecule's path is unpredictable, Yet pressure, the ideal gas law, and evaporation rates emerge as exact averages over roughly 10 to the 25th power of them. Everything is thermally dancing. This dissolves the paradox left by Chapter 2. Cells are exquisitely ordered, heat destroys order, and yet life needs warmth. The resolution is that order and the dance coexist at different scales. Here is the generative primitive you carry forward. The macro world looks lawful only because large N smothers the fluctuation. Shrink to the nano world, where N is small, and the dance stops averaging out and starts dominating. That is why it is a different place. This part explains why physics gives up tracking individual particles and predicts the swarm instead. The single move of the chapter is that you cannot track 10 to the 25th power molecules, and you do not want to. Exactly where only the distribution is knowable, physics turns sharp. Heat is that random motion, so the nano world is a violently dancing place. The surprise the chapter exists for is that this violence is survivable, information-wise. Nelson's line, "Everything is thermally dancing," sets up how a cell holds your genome intact amid the storm, and how physical reasoning intact amid the storm, and how physical reasoning inferred a linear chain database molecule before DNA was ever seen. The generative primitive is this: give up the trajectory, keep the statistics. Two constraints: normalization and finite spread. Make the average exact. From there, you predict the next case: pressure, evaporation, reaction rates, all the same trade. This section explains how one microscopic mechanism produces two large-scale effects, diffusion and friction, and why they are bound together. One mechanism wears two faces. A particle in a fluid is kicked incessantly by its neighbors. Those same random collisions that spread an initially localized population outward, which we see as diffusion, the growth of variants also drain any directed motion. An external force imposes, which we see as friction, the decay of the mean. Nelson's chapter exists to bind them. The diffusion constant d and the drag coefficient zeta are not independent material properties. They are two measurements of one underlying random walk, locked together by the relation that the product of d and zeta equals Boltzmann's constant times temperature. The deeper move is the focus question. The collective activity of many random actors is predictable even when each single motion is not. Determinism is recovered statistically from below. Friction is the visible residue of microscopic disorder eating macroscopic order. This part explains the single generator behind every dissipative process. The random walk. Friction, the diffusion of ink, heat conduction, electrical resistance, each one is organized. Energy ground into disorder by collisions with a vast random environment, and each obeys the same statistics as a drunkard's steps. The surprise this chapter buys is its focus answer. Individual molecular kicks are unpredictable, yet their collective is sharply predictable. Some enough independent randomness, and the average obeys a clean law. That is why a nano-world where everything jitters can still be quantitative. In cells, the actor is a single molecule, and KBT is no longer negligible, so this statistical regularity is the only predictability there is. This part explains why life at the scale of a cell obeys a different mechanics, and why the whole story follows from counting the time derivatives in the equation of motion. Count the time derivatives in the equation of motion. That count is a parity under reversing the sign of time, sending t2 minus t, and the whole chapter falls out of it. Newton's law, F equals ma, carries two derivatives. 2 is even, so the reverse trajectory still solves the same law with the same force. The macro world is reverse trajectory still solves the same law with the same force. The macro world is reversible. In the cell's nano world, water is effectively molasses, inertia vanishes, and force balances velocity. The law becomes F equals zeta times V, 1 derivative. 1 is odd, so time reversal is broken. The structural consequence is this. Any out and back shape change exactly undoes itself, and the net displacement is 0. This is Purcell's scallop theorem, and Nelson's paddle swimmer makes the same point. So a bacterium cannot row like a fish. It must break the symmetry with a rotating helical flagellum or a non-reciprocal ciliary stroke. Why? Bacteria swim. Unlike fish, reduces to the parity of a derivative count. This section explains the mechanical regime that a swimming bacterium lives in. At a bacterium scale, the inertial term vanishes from the equation of motion, and what remains is the chapter's entire thesis. Force no longer buys acceleration, it buys velocity. Drag balances applied force instantaneously, so the moment you stop pushing, you stop, coasting less than an atomic diameter. The Reynolds number measures exactly this ratio of inertia to viscosity, and below 1, the fluid has no memory. The deep consequence is time reversibility. The governing equation is symmetric under dA, going to minus t, so any reciprocal back and forth stroke retraces itself and nets 0 displacement. This is Purcell's scallop theorem. Swimming demands a non-reciprocal cycle. This is the mechanical regime every later chapter on motors and transport silently inhabits. This section explains why conservation of energy is not enough to predict what a machine can do, and names the second quantity that governs extractable work. Conservation alone underdetermines a machine. If energy never vanishes, 2 engines burning identical fuel should perform identically, yet they don't. So the chapter makes a wager. Besides energy, a second ledger governs what work is extractable, and unlike energy, it isn't conserved. That ledger is order. Friction, diffusion, every dissipative process the earlier chapters met shares one signature. They erase order, never restore it. The first law conserves energy. The second gives order a direction, downhill only. Free energy is the residue, the fraction of stored energy still redeemable as work, set by how much order survives. Entropy will be the measure, temperature, the exchange rate. The chapter's task is turning that picture into precise equations. This section sharpens why energy conservation, true as it is, never tells you what a system can actually do. Energy is conserved. The question the chapter sharpens is why that conservation never tells you what a system can do. Nelson's move is to install a second ledger beside energy, disorder, made quantitative as the bit count needed to specify a message. Written as a formula, the information I equals k times the natural logarithm of omega, with Shannon's formula being its weighted form. Unlike energy, this ledger is not conserved, and it is the gatekeeper. The free energy is precisely the slice of energy not mortgaged to disorder, the part still able to act. So efficiency differences between devices, impossible to read under conservation alone, become legible. 2 devices hold equal energy but differ in how much of it order leaves spendable. The chapter's telos is turning. Chapter 1's woolly disorder into this measurable, work-controlling quantity. This section explains how a force can arise with nothing pulling. A force need not come from anything pulling. Take the same move that gave gas pressure. Pressure is just the negative derivative of free energy with respect to volume, the system sliding downhill in free energy as the piston shifts. Now let the coordinate be anything biological: a cell's water content, the gap between two surfaces, the position of a macromolecule, a consent, the gap between two surfaces. Wherever displacing that coordinate changes how many microstates the system can occupy, the negative derivative of free energy with respect to it is a real, measurable force. There is no potential behind it, only the drive to raise entropy. That is the chapter's whole claim. Osmotic, depletion, hydrophobic and screened. Electrostatic effects, the short-range surface interactions that give enzymes their specificity, are one machine. They are gas pressure generalized. This section explains why a force does not need to live inside a bond between particles. Start from the freshman definition. Force equals minus the derivative of potential energy with respect to position. Swap potential energy for free energy, so force equals minus the derivative of free energy, with resulting force is entropic. And a whole class of pushes appears that no two particles exert on each other. The system simply slides downhill in free energy, where free energy equals energy minus temperature times entropy, where the slope is carried by entropy. The resulting force is entropic. The chapter's anchor is osmosis. Solute, trapped behind a semi-permeable membrane, drives water across, and the equilibrium pressure obeys the ideal gas law unchanged. The crowded water drops out, and the dilute solute behaves like a gas in vacuum. One derivative subsumes pressure, electrostatics, hydrophobic, and depletion effects. Force is what free energy does as you move a coordinate. This section explains how a chemical force arises from a difference in composition rather than from a difference in location. A force needs a difference. What it does not need is a place. Chapter 7. Built forces from differences laid out in space. Heat across a boundary, concentration across a membrane. Nelson's move here is to relocate the gradient into composition. Chemical potential, written mu, is of per species temperature, the availability of one molecular kind. Its imbalance, mu1 minus mu2, is itself a force, even when nothing varies from point to point. So, a machine adrift in a well-mixed solution still extracts work. Well-mixed in space differs from settled in reaction space. Far from equilibrium concentrations carry the free energy. Fold bond energy into the free energy. F, which equals E minus T times S, and self-assembly becomes ordinary downhill motion, paid for elsewhere in entropy. This part shows how chemical potential is temperature's twin, built by the same move applied to a different quantity. Temperature is the entropy derivative conjugate to energy. Chemical potential, written mu, is that same construction shifted one slot over, the entropy derivative conjugate to particle number. That single transposition is the whole chapter. Where matched temperatures stall, heat flow, matched mu values stall, particle flow, and a mismatch, mu A minus mu B, is the entropic force that moves molecules. The payoff resolves the focus question. A machine adrift in a well-mixed solution still extracts work, because well-mixed does not mean equilibrium. Many species held at far from equilibrium concentrations carry a chemical force that needs no spatial gradient. Fold each molecule's internal bond energy into the E of the free energy expression, F equals E minus Ts, and chemical energy becomes ordinary, free energy, convertible with every other form. That convertibility is what powers self-assembly. This section explains how macromolecules turn weak, individual bonds into crisp, switch-like behavior. Nelson's chapter answers one dissonance. Individual weak bonds should leave a macromolecule as floppy and thermally smeared as a gas molecule, yet proteins snap crisply between definite conformations, like furniture. The resolving primitive is cooperativity. Each monomer pays an energy penalty for disagreeing with its neighbors, so the chain cannot flip one unit at a time. It commits nearly all at once. That nearest neighbor coupling is what converts a gradual, gentle response into a sharp, switch-like transition, manufacturing macroscopic decisiveness out of microscopically weak parts. The same move sharpened the Michel transition back in Chapter 8. Here, it generates hemoglobin's sigmoidal oxygen binding, the helix-to-coil transition, and DNA melting. The deep point is that sharpness comes from agreement among neighbors rather than from stiffness in the parts themselves. This section explains why a floppy molecular chain can still behave like a clean switch. A floppy chain of weakly bound monomers should be as noisy as a gas, yet proteins snap cleanly between fixed shapes. Cooperativity dissolves the paradox. When each unit pays an energy penalty for disagreeing with its neighbors, purely local coupling converts a gradual response into a near-discrete switch. The chain flips almost all or nothing as a force or a chemical condition, crosses a force or a chemical condition crosses a threshold. This is the Ising move, collective sharpness manufactured from nearest neighbor agreement, with no global controller. The chapter's job in the book's arc is to reconcile its two faces of matter, molecules as chaotic gas against molecules as engineered machines. It hands you the one primitive that later renders allosteric proteins and the helix-to-coil transition predictable. This part explains how a single molecule turns a number into a direction. A scalar cannot point. Yet kinesin spends chemical bond energy, a single number called delta G, and walks one direction along its track. The move the chapter isolates is that the molecule does not push. It tilts a free energy landscape whose downhill direction is fixed by the geometry of the motor plus its track, then lets thermal collisions diffuse it down, that slope, a biased random walk. Direction lives in the geometry. Energy lives only in the tilt. The scalar sets how steep the slope is. The structure sets which way it runs. This is where the book's running theme, organisms as free energy transducers, finally acquires its mechanism, a molecule brokering between the chemical and the mechanical worlds, built by adding to ordinary macro-world mechanics exactly one ingredient: thermal motion. This part explains how a scalar quantity, something with no direction, gives rise to directed motion in a molecular motor. A scalar carries no direction. Chemical free energy is just a number, written delta G. Yet kinesin walks one way down, a microtubule. The whole load of the chapter is this, how a number becomes an arrow. The trick is to add one ingredient to ordinary macromechanics, thermal motion, and let the motor rectify it. The molecule already jitters in both directions. Fuel, that is ATP, tilts a free energy landscape whose slope is fixed by the geometry of motor plus track, so the random walk becomes biased. Direction is borrowed from the asymmetry of the structure, not manufactured by a push. Scalar to vector is broken symmetry. The geometry of the landscape is the only thing that knows which way is forward. This section explains why a living cell's membrane holds a standing concentration gradient. A concentration gradient that persists is a machine running. Left passive, the cell's interior, which is ion-rich and unlike the world outside, would relax toward dawn in equilibrium, drawing water in until the membrane bursts. It does not, because the membrane is studded with molecular machines that ferry ions against their gradients, paying in ATP-free energy, holding the cell in a non-equilibrium steady state whose voltage signature is the resting membrane potential. The chapter's move is this. Physicists inferred these pumps from osmotic and electrical arithmetic long before biochemistry named them, the same indirect attack that fingered DNA before its chemistry. The generative rule, every standing gradient across a membrane names a pump, spending free energy to sustain it. This section explains why a cell's resting state is something the cell has to pay for. A cell's interior should not exist. Its ionic composition is a concentration cliff that osmosis and diffusion strain to flatten, bursting the membrane as they go. It persists because the cell pays. Molecular pumps in the membrane burn metabolic free energy to drag ions uphill, holding a state kept far from equilibrium. The resting membrane potential looks like a static battery, yet it is a flux balance, leak against pump, dissipating continuously. That is the chapter's primitive. The living resting state is a non-equilibrium steady state, purchased, never a point settled into for free. Deneuve's potential names where the cell would relax to in death. Its distance from that value measures the pumping that keeps it alive. This section explains why a nerve impulse survives a long journey and why a nerve behaves unlike a wire. A wire transmits a signal it was handed. Bathed in conductive fluid, an axon would bleed any such signal out within millimeters, pure dissipation. The pulse survives because the membrane is excitable rather than passive. Each patch, once its voltage crosses threshold, throws open voltage-gated channels and spends its own stored ionic gradient to drive the neighboring patch past threshold in turn. The impulse is therefore regenerated at every point, never merely conducted. It is a self-propagating wave carrying its own fuel, like flame creeping along a fuse. Nelson's focus question is how a leaky cable carries a sharp signal undistorted across a meter. The answer is that non-linearity converts the leak into a relay. This part explains why a nerve cannot work as an ordinary wire, and what single change turns it into something that can carry a signal. A nerve is a bad wire. It leaks and it sits bathed in conductor, so a passive signal dies within a millimeter. The linear cable equation admits no traveling pulse at all. The chapter's single move is to break that linearity. Let the membrane's conductance depend on its own voltage, and the cable becomes an excitable medium. Every patch of membrane already holds energy that the passing pulse merely triggers, so the signal regenerates itself downstream, undamped. The impulse is continuously recreated as it travels, rather than carried along intact. This is burning fuse logic instead of copper wire logic. Each point along the nerve relights the next. This localizes the book's founding theme from Chapter 1. Organisms flush energy to defeat dissipation. Information transport, like muscular contraction, is work paid against entropy. The same accounting, a different output. This section explains how the whole book reduces to one method, and how the epilogue measures that method's reach by what it leaves untouched. The entire book collapses to one move, building simple models of complex phenomena. The epilogue fixes the reach of that method by its complement. It lists what a physics of energy and information cannot touch, rather than what it conquered. The ant is the anchor. You can now estimate why an ant hauls many times its own weight, while an elephant cannot. Yet its gait, its food, signaling, its nest, sociology, even one cell's biochemical choreography all escape the lens. The boundary itself is the lesson. A model is defined by where it stops. Nelson names the master key. He steps past evolution by natural selection and the conjecture that a common modularity underlies every self-organizing system. He leaves the composition itself as the reader's exercise. This section explains how the final chapter closes the book by naming what it could not reach. The epilogue defines the book by its complement, not what was explained, but what the method could not yet touch, the choreography of walking, the sociology of ants, the biochemical decision networks inside a single cell. The structural move is to convert the whole book into one transferable, primitive, complex phenomena through simple model building and then hand it over, saying, "Now it is your turn." The facts were never the deliverable. The estimation habit is, everything before this chapter was a vehicle for that one skill. Nelson names the single principle that would extend the method past its current edge, evolution by natural selection. He conjectures a common modularity threading through protein folding, metabolic self-organization, the brain wiring itself, language, and the origin of life. The chapter's work is to leave you generative. Its aim was never to leave you merely informed.